Stan Gibilisco here, proprietor and operator of amateur radio station W1GV Whiskey 1. Good vibrations at your service to talk about phased vertical antennas and just offer you a couple of examples of how this type of a system can provide some directivity, meaning directional characteristics, and also a little bit of gain. Imagine that you're looking down from high above, straight down onto two quarter wavelength vertical antennas, all over perfectly conducting ground, or over ground with a whole lot of radials buried in it so that it is perfectly conductive for all intents and purposes. So suppose now that these two antennas are spaced exactly a half a wavelength apart. Now this half wavelength is a free space half wavelength. There's no velocity factor involved. So on 80 meters, that would be about 40 meters, or a little over 120 feet. On 40 meters, it would be about 20 meters, or somewhere in the neighborhood of 70 feet. I guess on 80 meters then, it'd be 140 feet at the bottom of the band and maybe 120 feet at the top of the band. But you managed to figure out, using the formula for a half wavelength in free space, the distance in feet equals 492 divided by the frequency in megahertz, or the distance in meters equals 150 divided by the frequency in megahertz. And suppose that you feed these two vertical antennas exactly in phase with each other. What kind of a situation are you going to get? Well, first of all, you're going to get a low impedance at your feed point. You might say you connect them with equal lengths of coaxial cable, and then that goes to your radio. Each antenna has approximately 37 ohms of purely resistive impedance at the feed point, and they're going to appear in parallel because you're feeding them in phase, so you're going to have only about, well, what would that turn out to be? About 18 and a half ohms. That's going to be kind of a mismatch problem, so you're probably going to want to have some kind of an impedance matching transformer or transmatch at this point here where these two lengths of line join each other. But anyway, suppose that you manage to get that impedance to 50 ohms. What's going to happen? These two antennas are in phase. Well, off of either side, that is, if you look at the antenna from either side, let's say that north is straight towards the top of this illustration. So in the north and south directions, distant stations are going to see these two antennas in phase with each other. But towards the east or the west, stations far off in these directions will see these two antennas out of phase, exactly 180 degrees out of phase with each other, because it takes a half cycle worth of time for the signal to get from this antenna to this antenna, and then the combined signal to go off in this direction. And the same thing happens in the other direction. It takes 180 degrees or half a cycle worth of time for the half a period of the wave for the signal to get from Y to X and then off in that direction. And as a result, these two signals from X and Y are going to look 180 degrees out of phase, and you're going to get a null in these directions. So you're going to get a kind of a bidirectional radiation and response pattern here. Interesting. So what you're really going to see then, if you wanted to plot a directivity plot of this, you would see a sort of a figure 8 like that. Do that over again. You would see a figure 8. Well, this is a magic program, isn't it? It takes away and it gives back. But you get the idea, don't you? You're going to get a bidirectional radiation and response pattern. That's just one example of how phased verticals can work. There are a lot of other ways to do this. You might space them a quarter wavelength apart and then feed them 90 degrees out of phase. Then you would get a unidirectional pattern. And you would end up with a little bit of gain in either case, in either the bidirectional or the unidirectional pattern, and you would also get directivity. This phased vertical technique is not used that often anymore by amateur radio operators, but it is still used in low frequency broadcasting and medium frequency broadcasting, such as the standard AM broadcast band, where you need towers in order to make a vertical antenna. At it's 830 kilohertz. You're going to need a pretty tall antenna for a quarter wavelength, and so you're going to have a tower, and you might want to reach listeners to your north and your south much more than you want to reach them towards your east or your west, and so you'd make a phased array like this. So this can be taken advantage of to some extent, particularly now if you like to operate a lot of DX, or if you have a schedule with someone on 80 meters who happens to live in, say, let's just say that person lives in Texas and you live in Minnesota. You would probably build a phased array like this, or you might build a unidirectional array so that the antenna would favor the direction that you want to talk to that person in. This, of course, would be much more practical on a low band like 1.8 or 3.5 megahertz. If you're going to go on a band like 14, 18, 21 megahertz and higher frequencies, you'd probably end up using rotatable antennas such as the Yagi or Quad to get the results that you want. Stan Gibilisco, W1GV, Whiskey 1 Good Vibrations, signing off for now, saying 73 and so long, and hope you got a little bit of entertainment out of the way this program behaves. So long.